Hi, everyone. My name is Elsa Tang, and I'm a PhD candidate at UC San Diego, working with Dr. Karen Sandstrom. And today I will present our work on investigating the drivers of CO to H2 conversion factor variations in nearby galaxy centers. So our motivation is to study the CO to H2 conversion factor, or alpha CO. So this factor is defined as the ratio of the H2 mass over the CO1 to 0 luminosity. And this is a critical parameter to tracing molecular gas and star formation, because we know that CO has been the most commonly used tracer for the bulk molecular gas. However, alpha CO actually varies within and between galaxies, and it is known to depend on gas properties like temperature, densities, or metallicities. So, for example, this upper right plot here shows that alpha CO values can vary up to orders of magnitudes in different environments. And also, you can see that for galaxies like ULERGs, which have more extreme gas conditions, they usually have lower conversion factors than the commonly assumed Milky Way value. And interestingly, recent studies have also shown that alpha CO tend to be lower in the central kiloparsec of many nearby star-forming galaxies, which is probably related to more complicated environment or like nuclear activities in galaxy centers. But it is still not fully understood that what physical conditions are causing these alpha CO variations. And it is important to understand these alpha CO variations because, as I just mentioned, alpha CO is tied to both the amount and properties of molecular gas. And to be more specific, here I list some critical parameters that are commonly used for studying molecular clouds and star formation. So as you can see, all of them here depend on the molecular gas mass. So this means that alpha CO variations can have great effects on estimating these important quantities or on any star formation properties inferred from these quantities. So to study the environmental conditions in galaxy centers and understanding what physical process caused these alpha CO variations, we selected 3 nearby barred galaxies that were found to have lower alpha CO in the central kiloparsec regions. And to measure the gas properties and alpha CO in these centers, we cannot rely solely on the 12 CO lines because we need optically thin tracers like the CO isotope logs. So with Alma, we observe multiple 12 CO, 13 CO, and C18O lines toward the central 2 kiloparsec regions, which is shown by the red boxes in these images. And for further joint analysis, we match the beam size across all 6 lines to about 100 parsec, which corresponds to the giant molecular cloud scales. And here is our observed moment zero maps and line ratios for NGC 3351. So one notable thing about this target is that there is a star-forming ring around the nucleus in about the central 1 kiloparsec. And this ring connects with the 2 inflow arms that is driven by the stellar bar. And also, interestingly, in the line ratio maps, we can see that these bar-driven inflows have significantly higher CO to 13 CO ratios, and actually also the CO to C18O ratios. And I'll talk more about this later. And let me also quickly show the other 2 galaxies. So this one is NGC 3627, which is a more inclined galaxy, but we can clearly see a compact nucleus that is very bright in all 6 lines. And you can see that the nucleus is also showing distinct line ratios from other regions, which is quite different from what we saw in the previous galaxy. And another galaxy is NGC 4321, which is more face-on. And here we can also see that the line ratios in the nucleus also stand out from the inner spiral arms, which is suggesting different physical conditions between these regions. And so to determine the gas properties in different regions of these galaxies, we use non-LTE radiative transfer to model the intensities of all 6 lines we observe. And then we fit with the line intensities to find out the best fit solution, as well as the 1D and 2D likelihood distributions of each parameter. So the modeled parameters include the CO column density per line width, kinetic temperature, H2 volume density, and the 2 CO isotope log abundances, and also the beam filling factor. So our modeling is done on a pixel by pixel basis. So this means that for each pixel, we extract the highest likelihood solutions of each parameter. And then by iterating through all the pixels, we can generate a map like this, which shows the highest likelihood physical conditions at each pixel. So in these maps, we can see like the variations of multiple gas properties. So for example, here you can see the kinetic temperature is higher near the nucleus and the contact points in this galaxy. And actually, the temperature is even much higher in NGC 3627. And also in 3627, there is a clear density enhancement toward the nucleus. And these are also seen in NGC 4321 as well. So after constraining these physical conditions, now we can also derive the alpha CO distributions from our modeling parameter and also the predicted CO intensity. And then again, we generate the pixel by pixel alpha CO maps shown here. So more clearly, we can see in this plot, we show a cross comparison among 3 galaxies of how alpha CO varies with the projected heliocentric radius. So as we can see, almost all pixels across our observed regions have alpha CO lower than the standard Milky Way value. And generally, we can also see that alpha CO decreases slowly with the radius in the inner 1 kiloparsec region at around a value that is about 3 times lower than the Milky Way alpha CO. But more interestingly, in NGC 3351, there is a big drop at about 500 parsec, which is actually just where the inflow arms and the nuclear ring intersects. So this means that alpha CO is significantly lower in the bar-driven inflows. And to discuss how these derived alpha CO depends on the physical properties, first, we find that the radial variation of alpha CO is similar to the radial profile of the CO optical depth, which suggests a strong dependence between alpha CO and tau CO. And because optical depth is proportional to the column density per line width, this means that gas concentration and turbulence or shear effects are playing important roles in setting the alpha CO in these regions. However, we also find that the alpha CO trends are diverse in the very center nuclear regions. And as you can see, the trend here is actually somewhat different from the optical depth trends. So this means that there must be other factors in addition to tau that is also playing a role. So if you recall, our modeling do reveal denser and hotter gas in the nuclei. So it is likely that the highly excited conditions in these very compact nuclei are also driving the alpha CO variations. And finally, it will be very useful if there are observables that can predict where alpha CO variations may exist. So using NGC 3351 as an example, we already see that there are substantially lower alpha CO and tau CO in the inflow arms. And we think that this can actually be supported by the observed line ratios and line widths. So as we can see, the CO to 13 CO line ratio is significantly higher in the arms, which means that there is more CO emission per unit gas mass. And this, by definition, would give a lower alpha CO. But interestingly, we also find higher velocity dispersions in the arms, which may suggest more turbulent environment, or maybe the existence of shear in these bar-driven inflows. And this higher velocity dispersions will lead to lower CO optical depths in the arms. So the reason for such low conversion factor in these arms is likely because of the lower CO optical depth that leads to more fraction of the escape CO emission. And this can be reflected in the CO-to-13CO and even the CO-to-C18O ratios as well, and also reflected in the line width. So as a summary, this final figure here combines our modeling result for all three galaxies, and we can see a clear and positive correlations between alpha CO and tau CO. And here, by color coding these points with the binned medians of the observed CO-to-13CO ratio, we can see that this ratio is generally tracing the tau CO inversely. So we think this line ratio can be a useful observational tracer for alpha CO variations, especially in galaxy centers where the tau CO variations are more dominant. And lastly, it is also clear that almost all regions have alpha CO lower than the standard Milky Way value, which we think may be due to the overall higher velocity dispersions in barred galaxy centers, because this higher velocity dispersion would decrease the CO optical depth and thus also decrease the conversion factor as well. So I'll end my talk here, but if you are interested in more details, feel free to contact me, or you can also take a look at our published paper on NGC 3351. Thank you very much.